फुल स्क्रीन कर दे, डबल टैप।
So in this KSoM special seminar, we have Manika Gupta for this session.
Previous talks we have seen applications, checks which is the lower bound of representation of the number as a sum of a prime and a number which is at most the product of two primes. And we also saw Chang's theorem, which says that which gives a finite fixed distance between primes. It says that infinitely times you have primes which are some finite number apart, and that number is something less than 70 million. And of course, that number was continuously improved, also using seed theory. So in this talk, we'll see yet another application of seed theory, which is factorization of integers. So, factorization of integers. Using seed theory. So, factorization of integers is a big problem in number theory and in computability theory. So, there are two problems. One is testing the primality of a number to test whether the number is prime or not, and to factorize a number into primes. And to test whether a number is prime or not is a relatively easy problem because we know that. So, there are many tests available for that. Miller-Rabin test or the AKS primality test. And we know that at least one of them can be done in polynomial time. So, for testing whether an integer is prime or not is a relatively easy problem. But factorization of integers into primes, into its prime factorization, is considered to be a relatively hard problem. We don't yet have an algorithm that can be completed in polynomial time. But if we do find an algorithm that can be completed in polynomial time, then it will have some implications for cryptography and other areas because in
Credit cards won't be safe. No, one minute.
So, AKS algorithm is a deterministic algorithm to find whether a number is prime in polynomial type. And then other test is that you have mentioned, it's like a probabilistic one.
yeah,
So
so it's
not deterministic.
and it's not even in polynomial time. So it's not in polynomial time.
Even factorization of integers is not in.
No, I mean you can't complete it in polynomial time.
Actually, you have to determine how much accuracy you require and do it. If you are happy with 50% accuracy, you can finish it in one step. And if you want the 75, you go for 2 steps and like that.
So as the accuracy increases, the time.
So regarding the cryptography thing, there is this old algorithm or protocol for public private key exchange. Private key exchange algorithm. That's Diffie-Hellman. So there are two problems which have not yet been solved for certain groups, like groups of rational points and elliptic curves. So those two problems are discrete logarithm problems and this factorization of integers. So if you solve this in efficient amount of time, then your credit card won't be safe anymore. That's what I was trying to say.
The most popular security algorithm nowadays is RSA, and that uses so it uses two very large.
For example, RSA laboratories timed down announce a number, and if somebody factorizes that number, they get a huge prize money.
So one of the seeds that we'll be talking about, general field seed, is one of the most popular seeds that is used in most contests where they announce it. So whenever they are most people attack it was the general number fields. So how do we figure out this problem? It's the content of this talk today. So the most efficient classical algorithm that we know right now to factor integers which are larger than 12, which is 10 to the power 100, is the general number field. But we will be discussing a simpler and a little less efficient version of the general number field C, known as the rational C. So in the rational C, say that n is the number that we want to factor. We will pick a subset of n of z mod nz as a factor base, which will be a set of primes such that p is less than b. And what is this b? We will choose b. We will choose an appropriate integer b. Which will be known as our limit. So this is the set. We have an n, which is the number that we want to factor. We have a factor. We have a integer b, which is known as our level, and we have a factor base, which is the number of primes which are less than or equal to b. So in a previous talk, we've already learned about what are smooth numbers. Now, if I say a number is b smooth, it means that its largest prime factor is less than or equal to b. So in this C, our purpose will be to find a numbers that such that Z and n plus Z are b smooth. Or in other words, Z and n plus Z don't have prime factors larger than b. So before we discuss this in further detail, we will explore the problem of factorization in general. So one of the most naive methods that we know of factorizing an integer is to keep dividing it by all the primes up to, say, if you want to factorize n, we will take root n. Up till root n, we will try each and every prime factor and we see whether or not it divides it. That is how we learned how to do prime factorization in like elementary classes. But if you see that if you have a number with say 50 digits, say in order of 10 to the power 50, then to test all the numbers till root 10, you will have to test all the primes up to 10 raised to the power 20. So this can easily take thousands of years. So we need to improve on this method for sure. So most modern techniques of factorization use the same underlying principle coming from number theory. So the number theory doesn't really get that much more complex as we go to rational C, with a little bit more modern methods. And the technique that we'll be using is known as Verner's square congruence method. And this method is very simple. What it says is, say you start out with a pair x, y such that x is not equal to plus minus y not equal to. And x square is equal to y square. So suppose you have a pair x, y. So you can use this pair to come up with factors of n. How? Just take y to the other side, you have x square minus y square is equal to 0 model. So you have x plus y, x minus y equal to 0 model. Now notice that this product definitely has factors of n, but this product can also be trivial. So it can be something like n into 1 or 1 into n, right? So to generate trivial factors, we take GCD of x plus y and n and GCD of x minus y. Notice that none of these can be 1 because we say that x is not this. So this will give us non-trivial factors. So most modern factorization algorithms are just about finding these suitable pairs. But before that, if you want to see an example of how this square polynomial works, just take an example. Well, if you know what square polynomial is, one square mod a little bit more in volume, if 1649. So notice that I've already supplied these congruences. So getting to these will be a major part of our rational series. No, there is no square. This is an example of even if you don't have squares, but you have multiple congruences, how can you manipulate them to get into this one? So okay, so how can we multiply these things to get a square congruence? So we know that 32 is 2 to the power 5. We know this is 5 square. So we can combine these two. Just we want even powers on the right hand side. So we can combine. We already have here. We have a 3 and a 5 here. So we can combine these two to get 41 into 23 whole square is equal to 2 to the power 3 plus 5 will become 8. 5 square 1 6 1 8.
माइनस देखना पड़ेगा ना प्लस माइनस देखना पड़ेगा ना कि इट्स नॉट इक्वल टू प्लस माइनस ऑफ दैट
Yeah, if we don't get non-trivial factors, then we can worry about that. But
So Manika, what is your algorithm Have you explained your algorithm
No.
now? No.
Explaining one of the
Math example.
lemmas which is used in the algorithm. So these and finding GCD is not a big problem.
Logarithmic time में होता है क्या? Is that it does. Does that happen?
Which one?
Euclid's algo, is it log? What is the complexity?
And
of-
there is complex.
That is polynomial.
Yeah.
So coming back to our algorithm. We want to find these pairs, X and Y. So this is one of the problems. We want to find Z such that Z and N plus Z is B. Now there are many algorithms for this purpose also. Because just think of this as finding N plus Z such that N plus Z is B smooth and Z is less than equal to QB. Because that will ensure that Z is Z is less than equal to B square. Because that will ensure that the prime factors of Z will be less than equal to B. So in the given range N to N plus K, where K is less than equal to B square, we have to find numbers which are B square. And if we choose a small enough b, this can be done in small enough time. Because all you have to do is you have to check for each factors, but only for k numbers. So if you choose a small enough b, this can be done. So now we assume that we have numbers z such that this happens. And we have to do this how many times? Generally, it is sufficient if we find Z, if we find mod p number of z's. Because finally what we want to do is, since we know that n plus z and z are, so n plus z is equal to z mod n, right? So we will be using this concept to generate these square. And if we have these many square complexes and we construct them in a matrix, you'll see that you have more rows than you have columns. And so you will find some linear dependence between those relations, and you'll be able to come up with, hopefully, you'll be able to come up with these even powers every time. This is also not guaranteed, but we have seen that it happens with a very high percentage. So what?
No. You wrote there, no? Mod B mini congruence relations. What was that B? That's it.
Just
You just whatever you rubbed right now,
okay.
you wrote mod. No. You said.
So I want the number of such threads so that should be
What is that B?
there
That
is hardly of this that we have. So see that Z is equal to some, because Z is so like this. confirmation. Is the user have a break? Here R is the cardinality of T, and P is the number of these. So our aim is to combine these confluences that we get into a way such that all the prime powers will be even. So I'll show through an example how we can do that. And I'm going to back to do this. We'll choose a level. So a very typical level is 7 because it is also saying that many numbers are 7 square. Like if you so in the previous talk or just in general, you can see that as the notation of whenever I use x psi x t, which is the number of numbers which are these two less than equal to x is distributed like so a very typical level is 7. So we choose 7 here. So if B is 7, what is our P? P is order number. Cardinality of P. So we try to come up with any 4 confluences, or any 4 z's, such that z and 187 plus z is B. So we can employ an external algorithm to do that. Say we got 4 iterations. Okay. And based on these 4 z's, we get 4 confluences.
If they find, they have to factorize all numbers between n and n plus k.
That is just one very crude method to find that. There are also some other algorithms which can test for smoothness, smoothness.
Polynomial time.
Yes. And not all of them are 100% like they are not guaranteed to find.
Yeah, it might not exist. No?
Yeah, it might not exist, but even if it does exist, the algorithm might not be able to find. So they are not deterministic. So all this is like a heuristic way of factorization. So based on these, we give the confluences. 2 is confluent 189, 187. Five, 192. So, if you look at the prime factorization, then 2 is to 5 is 5, 3 minus 7, 3 6 2 cubed into 7. And on the right hand side, 189 is uh, what is 3 Okay. So now now next task is to combine these confluences to have even powers of these. So notice that we don't actually have to do anything because we already have a confluence which is of the form that no?
7 square.
Yeah. So the confluence is 3 square.
2 square.
This is what we do.
Okay.
But if we by chance we didn't have this, then you notice that you could have combined, say, you could have combined this one and probably
It's okay. Don't worry too much. So I am really wanted to see your algorithm. So
Yeah, this is the
so can you write it in a step-by-step process? It's like a step 1, step 2, step 3, etc. Like start and finish it.
this is something that we will get a pair as 3 and 14, and we can get GCD of 14 plus 3 and 187 as one factor, and GCD of 14 minus 3 and 187 as the other factor, and that is how we have. So if I write it in steps, then the rational C value is we have a number here. This you can use an example. So how many conferences?
20.
So I find T
P is something like B by log B, right? P is something like B by log B, right?
yeah, for large.
Prime.
But the thing is, we want to use
Small
small
ones.
g, so we can't really.
Small as in 7.
7 is the one we use Even if that is fine.
Maybe you can complete that. We can discuss. So we will be coming to the complexity of that.
Maybe use CI or something. Adobe.
Okay. But let it help us.
Even works. Plus minus like that. Plus minus.
Okay. Now you see that this is a deterministic algorithm, and then you get
No, because that is not deterministic. No, the smooth thing. The smooth thing. That she said is not deterministic.
It depends on what algorithm you use. If you use the one which tests for every till that point,
Yeah, yeah. That is not. That might not be polynomial type, or is it also?
depends on your B. How many?
So okay. Now the question is like, what is the complexity of this algorithm? Because once we have the algorithm, the most important things like the algorithm must take the minimal amount of time.
I think this is more than. I can write something. I think it's more than that.
No, what can you focus on that?
Calculate with.
So you see that you are choosing a level B. So see that this is your choice of B. That later it may influence like a chance of getting a prime factors, and you sometimes you may get or may not get it. So it's your selection of B is quite crucial there. So can you say something about the selection of B, which B can be an optimal one? No, the 7 in this case. So you see that if I have a generator, so I don't know how to proceed this algorithm. So what kind of B will be nice? Small, but if I take it to, then sometimes things may not work also. I want something like it will be working and I add some.
Yeah, so here are some pitfalls with this B. First of all, when you choose B, you have to choose this such that anything in that set P, primes less than equal to B, none of those primes should divide A. Otherwise, this
No, if I find a prime that divides n already, I have a prime done. So that is a trivial factorization case. For example, if it 2 to the power something is coming and then I just divide by 2, see, I can go a little bit further, and that is a trivial initialization. So
algorithm will also fail if your number is of the form p to the power k. But there are other algorithms for.
I understand. This is an extreme cases. In fact, extreme cases.
So the main reason that this algorithm is slow and not considered to be efficient is because
Well, I see that, for example, in RSA and various places, we use 2 distinct primes, a product of 2 distinct primes. We know that is almost equal size of thing primes. So in such cases, so whether usually we know the factorization of integers is the exponential time indicated. So in this method, you get some advantage. You can get it like a sub exponential, or it is still exponential or something. Maybe you can make that comment.
again, another thing that one of the reasons it's considered not as efficient is because of this reason, right? We want to search for z such that z plus n plus z is b. So we are also searching for n plus z, which is of the order n, right? So unless and until you are lucky and you can get this any external algorithm in which you are able to find such smooth, it will also be of order n. So it will be exponential, is what I'm saying. But in an improvement of this algorithm, as we see, is called general number field series, and that can get sub exponential. So that can get order of n because it directly lowers this number. So the upper bound, so we don't have to find smooth numbers of the order n. Now we only have to find smooth numbers of the order n to the power 1 over 2. So it will become sub exponential. So as such, this algorithm, I don't know if it is definitely better than naive algorithms, but it's still not as efficient as before.
You have some suggestions of like what kind of modification can.
Yes. So up till now we have used analytic number theory tools. Not even that, we used just elementary number theory. If we bring into the pictures of algebraic number theory, then we can get this time to be a little better. How can we do that? So this is the number field.
So that you said something about that matrix, right? That this has more.
Later complete number of things.
You take a movie. Then it is possible. Then if you let alpha be a complex root of f, can you know that there is a ring from z alpha? This is our appending alpha. Then what n, and this is determined by sending alpha to n. So this will be a ring. So for just for explanation, we'll assume that this is a unique factorization domain.
So first you evaluate. Oh, sorry. So this thing you first evaluate at m and then you do a mod n, right? Huh? So that there is z mod n z, right?
Yeah. Okay.
Okay.
So again, you choose B, and you will get some B. Now you can choose an angle of this base factor is Z alpha as well. So what that means is the factor base in Z alpha as well. So through this homomorphism, you can get a factor base in Z alpha, which will be a genuine, right? So now everything that we did here, we will do here. So what is our advantage here? Our advantage is that when we pick this m, we can pick this m to be much smaller than n. And based on the choice of m, this numbers that we had to find, smooth numbers of order n, now we will just have to find smooth numbers of order n instead. So this is just a general idea of how our number field set works. It can be, if you can choose the number field very carefully, which what I'm saying is this polynomial f that you choose, it will dramatically affect the efficiency of the algorithm. So because this choice is there. So choosing f is it is already better than this method, but choosing f can make the algorithm even more efficient. And if you choose it in the most efficient manner, then what you end up with is the general number fields and coupled with some more modifications. And that will get this n to the order n to the order n already. Then d is a positive integer and greater than. So you can get it in some explanation. Right? The complexity of the general number that we see is turns out to be this.
Whether this is the best known algorithm for factorizing, because in RSA and announces you don't like many people uses this kind of method. Whether this is the best known one or
This is the fastest classical algorithm. In this family, there are a couple of seeds. So you have rational.
Is there any reference for this?
so one more. She completed rationals. Which are the one rationals here?
You have rational seed. Then improvement on rational seed is quadratic seed. Then you have special number field seed. And then finally you have general number field seed. And this is the best known classical algorithm for factorization.
Your question answer session. There is a
Yeah.
Oh,
Reference for this. Okay. You said I could follow that. You said if you pick a suitable
one.
focus.
So let us thanks to the speaker. Like we should have a questions.
Yeah, she'll give me later. Maybe. Just a reference for.
So fine. Maybe Krishna also like to see it as well. So it's fine. So thanks to the speaker once again.
Forgot the answer. What did you answer to the question he asked? Is this the best? Don't think or this is the best.
But that's what I'm going to
So what M do they?
I don't know.
What M do they use? Usually.
You can theoretically pick any molecular polynomial in physics, but because this thing is there, right? You want to pick an M subset, f of M is 0, and you want to pick n or small. Based on that, you can modify it.